Welcome back. So in this video I'll be talking about another theory in the linear conservation of momentum. So that's the firing of a bullet. Firing of a bullet. So firing of a bullet actually using a rifle or a cannon or something like that is another scenario in which the conservation of momentum acts in a very funny way. So to find that, we'll find what happens when a bullet is fired through some firearm. So I'll take a rifle, the barrel of the rifle like this, right? I'll draw in the barrel of the rifle, right? So this is the barrel of the rifle, and I'll take the bullet as like this. Bullet like that, and I assume that the mass of the bullet is 200 grams. Mass of the rifle is 5 kilograms. It can't be so large, but if you're taking some like a cannon and like that, it can be 5 kilograms, right? So this is 5 kilograms. And if the velocity of this bullet is 100 meters per second, the question is asking, what is the velocity of the rifle? The velocity of the rifle will be in some direction, but to understand this theory, we have to, before marking the velocity, the direction of velocity of this rifle, we have to understand what actually happens when a bullet is being fired by this rifle. What happens inside the barrel? So if the bullet is being fired either by a spring or by explosion, what happens is that the bullet exerts some force on this barrel, because that force causes the bullet to move. That is a very large force, because you need a very large force for the bullet to travel such a long distance. You need a great acceleration, because after this leaves the barrel, this will go into deceleration. But in order to have some distance travel, say we need the bullet to travel a distance of 100 meters. To get that 100 meters, and when the speed is decreasing, the speed will not stay constant, because although the horizontal component will stay constant, the vertical component will go down, because the motion of a bullet is not only linear motion, it will also be a rotational motion. So it is a very complex scenario. So to have the energy for all those, we need a huge force inside this. So when the explosion or the spring gives some force to the bullet, this bullet will experience some force, so it will store that force. But initially the bullet is at rest. So he'll say, okay, what happened here? You gave me some force, but I was in stable equilibrium because I was at rest, but you made me unstable, so I will not forgive you, and I will give you a force in the opposite direction. So this has some force in this direction, the bullet. So the bullet will not stay like that until it goes. At the instant it got that force, it will exert a force in the other direction. So according to Newton's third law, the force and the reaction can't be on the same object, it should be on the other object, and if they are equal and opposite. So they should be equal and opposite means the force acts on the gun, actually it should act on the gun, and it should be in the opposite direction. So it is in this direction. Force on the gun, or the force on the barrel, or the force on the something like that, where it is explosion or the spring release occurs. So the force is in this direction. Now when you consider the whole system, the total force on the system is zero. So total force on the system is zero. Wow. So since the total force on the system is zero, we can easily put the conservation of linear momentum. Alright, so that's very simple now. Just another problem in conservation of linear momentum. So that's a very nice and very funny scenario. What's happening here? So the total force is zero, the conservation of linear momentum can be good. So I'll put, now there's no conservation, now there's no momentum in the the vertical direction. So the total momentum will be in the horizontal direction. So in the horizontal direction I will put the conservation of linear momentum. So I can write Pi equals Pf in this direction. Right? Pi equals Pf, so the initial horizontal momentum will be equal to the initial final momentum. So what actually happens is that initial horizontal momentum is zero, because both the gun and the bullet are initially at rest, so the initial horizontal momentum is 0. So now you must understand, if for the initial if the initial horizontal momentum is 0, initial final momentum should also be 0. If the initial final momentum is 0, the direction of the momentum will depend on the direction of the velocity. Now, I have already marked the direction of this velocity, direction of the velocity of the bullet as 100 meters per second. So, in order for the final momentum to be 0, the velocity of the gun should be in the other direction. So that's obvious. If you are firing, if you have actually experienced the firing of a gun, you will see that if the bullet goes in some direction, you will experience the force on you on the other direction. So the velocity of the gun or the barrel is in this direction. So I mark it this way, right? Velocity of the barrel or the gun. Alright, so I have the mass, I have the velocities. Now I need to find what is the velocity of the rifle. So that's very simple. Just another instance in which the conservation of linear momentum takes place. Just like two balls or two masses or two particles have been collided each other and they are going in the opposite direction. So the initial momentum is 0. So the final momentum of the bullet is the mass times its velocity. So the mass is 200 grams times its velocity 100 meters per second. Now the mass of the barrel or the mass of the rifle, actually the mass of the rifle has been given as 5 kilograms. Mass of the bullet has been given as 200 grams. Velocity of this bullet has been given as 100 meters per second. So we have these quantities. This 200 grams is not in the SI units. So 5 kilograms and meters per second are in SI units. So we have to find the velocity also in the SI units. So I'll convert 200 grams into SI units, which is 0.2 kilograms, and then substitute to find the final momentum of the bullet. Alright, so the final momentum of the bullet will be mass times its velocity, which is 0.2 kilograms times its velocity 100. So 0.2 times 100 in this direction. Plus the mass of the gun or the barrel is 5 kilograms. So and its velocity is v. So it's in the other direction. So its momentum will be 5 times v in this direction. So I'll take this side to this side. So it will become minus and change its direction so that both the momentums are in the same direction. So 5v is equal to, in this direction, is equal to 0.2 times 100 is 200. So v is equal to 40 meters per second. So if the mass of the bullet is 200 grams, its velocity is 100 meters per second in this direction, and the mass of the mass of the barrel is 5 kilograms, its velocity will be 40 meters per second. So what actually happens is, if initial momentum of the system will be 0, and if the mass of the this one, what actually happens is that mass of the momentum, according to this side, according to this equation, the momentum of the barrel or momentum of the gun or the momentum of that firearm will be equal to the momentum of the bullet. So if the mass of the gun is m, its velocity is v, and capital M and capital V, right? It should be equal to the mass, the momentum of the bullet. So I will take the momentum of the mass of the bullet as simple m and its velocity as simple v. Well, until u, because sometimes it may be confusing. So v is equal to mu divided by m. So what actually happens if you keep the mass and the velocity of the bullet constant and you increase m, you decrease v. So if the mass and the velocity of the bullet, so the velocity of the bullet should be the same, maybe the same, because the explosion provides the same force, so the velocity of the bullet may be the same, so the moment of the bullet doesn't change for a single gun. So what actually happens is that the momentum is same. You can decrease the velocity at which the gun is coming this side by increasing the mass of the gun. So that's obvious. If you are firing with a normal rifle, and if you're firing a cannon, you can easily notice that the normal rifle will experience more force and more velocity towards the other direction, and the cannon will only displace or go to the other direction in a very small velocity. Although the displacement may be same, the displacement, what affects for the displacement is the force applied. That means the acceleration. The displacement is affected by the acceleration, so that means the force applied. So I am not talking about the displacement in the distance it goes this side. The distance, this system, the barrel goes this side. I am talking about the velocity at which the barrel is going this side. So if you increase the mass of the barrel, you can see from this equation that keeping mu constant for a single barrel, when you increase the mass, you decrease velocity. So if you need a small velocity, or if you need a small force to act in this direction, what we should do is to increase the mass. So that's another application of conservation of linear momentum. So that might be the end of the series of lectures on linear momentum, applications of linear momentum. So I'll meet with you on another series of videos on physics on another topic on the next day. So thanks for watching this video, and I'm thankful for you watching the whole series of videos if you have watched those, and see you again.